Thank you so much, Elizabeth, and thanks to all the organizers for inviting me to speak. The program is, of course, very nice. It's a shame that not so many people were able to make it, but we're actually in Bonn, and at the Hausdorff Institute right now. And it's, yeah, very, very nice here. And the conference has been so nice also. And I wanted to say that, of course, the program is dedicated to Elizabeth Menkes, so that's also a special honor to be talking here. And yes, so I wanted to talk about the conjectural symmetric version of Ehrhard inequality. In the chat, in case of interest, I put two links, first of all to the preprint, and second of all to the slides, in case anyone's interested in scrolling the slides up and down. I always find it somehow more useful during an online talk, so you can go on the link and yeah, they're there. Let me recall a little tiny bit of notation. So there is the back measure that will be discussed a little bit. The Gaussian measure will be discussed most of all. I denoted this letter gamma. This is Gaussian density. Minkowski sum of set definition is written here. And I will often write the Gaussian CDF psi, which is written here. By the way, somebody pointed, well, it seems that I'm unique in denoting it by psi and everyone else is denoting it by phi, and I should probably change. I don't know, maybe I'm slightly dyslexic. I don't know. I always thought that everyone denotes it by psi, and then I discovered that in some places I saw it phi, and then I realized that everybody writes phi. Anyway, so this psi will be the notation for the Gaussian CDF. Let me remind you the Brun-Minkowski inequality. So the Brun-Minkowski inequality is a fundamental property, concavity property of the Lebesgue volume. It tells us that the Lebesgue volume is concave to the power 1 over n. So if we take a pair of parallel measurable sets and we take the average, Minkowski average, you can estimate it from below by the average of volumes, both of them raised to the power 1 over n. Very nice thing about the Brun-Minkowski inequality is that it implies the isoperimetric inequality. The isoperimetric inequality, classical isoperimetric inequality known since ancient times, tells us that of all the sets of fixed volume, the ball is the one that has the smallest perimeter. If you fix the volume, the perimeter is minimized on a ball. And one way to denote perimeter, to define perimeter, is precisely as written here, lim inf. I don't know if you can see. You cannot see my mouse, right? Can you see my mouse? No, probably not. So what if I do this? You can see, yes? No, thanks, Olivia. Okay, but if I do, never mind. Okay. Anyway, so here's the definition of the perimeter written down there, and if estimated using the Brun-Minkowski inequality from below, get the proof. It's pretty nice because particularly, yeah, I know, but it's still complicated. So thanks, Olivia. It's nice because Brun-Minkowski inequality is really particularly very easy to prove. Unlike the isoperimetric inequality, the proof of Lusternik from 1935, which is just like a probably high school exercise, one could say, modulo some measure theory. So yeah, it's probably the shortest way to get to the isoperimetric inequality. In analogy with this, in the Gaussian world, there is this thing called Ehrhard inequality, which is a very beautiful, very fundamental property of the Gaussian measure that tells us that if we apply the inverse of the Gaussian CDF that I defined earlier, compose it with the Gaussian measure and take Minkowski average of sets, it's bounded from below by the average. And again, similarly, there exists also the Gaussian isoperimetric inequality that tells us that for all parallel measurable sets of fixed Gaussian measure, the perimeter is always the smallest among them on a half space, on a left half space. And so to speak, the place where the half space meets the x-axis is psi inverse of A, precisely where A is the measure. This Gaussian isoperimetric inequality follows immediately from Ehrhard. Let me see. It's a little bit harder than in the Minkowski case because there is no homogeneity, and this time we need to send the ball kind of to infinity. So again, we write down the Gaussian perimeter is written here, and we write it. We introduce additional parameter lambda that we tend sorry, epsilon. Yeah, no, lambda that we send to 0 as written here, and then everything kind of works. And this limit written here equals to 1 because of concentration actually. So that's all very nice. Now let me briefly describe somehow the general idea behind this project and behind other projects, and a lot of people have been developing this general somehow direction, which in my opinion is very interesting. So let me just say the general idea that happens here. Suppose we have some measure mu, and we want to say that for some function f, this concavity holds. We compose a function with a measure, take a Minkowski average, and it happens to be concave. How do we understand, how do we derive such a property? So we view this Minkowski average as a perturbation, Minkowski interpolation sort of between sets. Particularly, we view it locally as a perturbation where t is very small. So we look at the set kt, which is exactly kind of like k perturbed slightly. We take the measure, apply a measure of it, u of kt, and the fact that this f composed with this measure is concave, it's just something one-dimensional. It's about second derivative of this one-dimensional function being non-positive. And if you compute things and you say, you assume that your function is increasing, usually for all such purposes, it's equivalent to saying that the second derivative of the function divided by the first derivative of the function at measure a, where mu of k is a, is bounded from above by something that depends on the derivative of the measure of the perturbation, which is a separate story. I'm not going to give any more details in this talk about this. Here slightly is a picture about perturbing k along the normal in the normal direction. That's what happens when you take Minkowski sum. Roughly speaking, this is how you can view it, at least in some geometrically intuitive way. So there's been a lot of work in this direction. You can discuss this history in many different ways. Colisanti deduced the local version of the Minkowski inequality in 2008 of the classical one. Kolesnikov and Milman wrote a series of papers, a particularly important one, and I think it's probably the most important paper in all of this framework, was the one in 2013 where they gave L2 proof of the Minkowski inequality. The importance of it is that they didn't just derive the equivalent sort of formulation, they actually found a way to prove it, and that's very, very nice. I studied this subject also in a series of papers with Colisanti, Marsighetti, Kolesnikov, and Fossil. Actually, also in my PhD thesis, in fact, I studied it also. I also had a proof of the Minkowski inequality, but only in dimension 2, a different one from the one that Kolesnikov-Milman gave us. I would say pretty different, just using Fourier analysis. Jenko and Leo Puterman had important contributions to this, and there is many more names. I will not be able to mention all of them. Let me jump to discussing this very tantalizing problem called Gaussian symmetric isoperimetric problem. It's a kind of problem that's somehow pretty easy to get obsessed with if you're a particular kind of masochist somehow, I guess. So Frank Barth raised this question back in the 90s. O'Donnell raised this question. Stephen Fehlman also raised this question. In fact, I believe he referred in his paper to this question as a conjecture of Morgan given to him in personal communication. So actually, maybe I should put the name of Morgan there. What's the question? So the conjecture is, if you have a measurable symmetric set, inherent symmetric means if x is in k minus x is in k, and the measure is a. Doesn't need to be convex, by the way. That's an important difference here. Then the perimeter is minimized on something that I'm going to call in the stock round case cylinder, which is a direct product of a space and the wall. So we have a k-dimensional wall of some radius. We have a n minus k-dimensional subspace. Take direct product, it looks kind of like a cylinder. So the perimeter is minimized either on that or on its complement. depending on the measures that we take. So it's, yeah, appears to be a natural and very interesting conjecture. A seemingly related question would be, in view of somehow the first two slides, is to ask what is the optimal function f for which for symmetric convex sets KNL, it's concave. It has this concavity property. And so I would like to conjecture, I think that the correct function to look at, I'm going to zoom in and specify a bit more what it is, but it has a form of being equal to these crazy special functions on a collection of intervals. So in other words, we can split the interval 0, 1 into a collection of sets. On each set, it's going to be equal to linear combination of beta k, alpha k, just some coefficients, doesn't matter, of this function jk minus 1 inverse of ck minus 1a. It looks really scary if you look, of course, at all this notation, but the geometric meaning of this, so this is, let me probably write, it's important. So this is the radius of the round case cylinder. In other words, if we have a round case cylinder of measure a, so the ball is of dimension k and the measure of it is a, the radius is given by that function. In that regard, it is very much parallel to Ehrhard's inequality. You can see definite similarity to Ehrhard, because in Ehrhard we have function psi inverse, which is, if you want, you can call it a radius of the half space, or it's not a radius, but it's something that corresponds to the distance of the half space, or to the fatness of the half space. So here we talk about the fatness of the cylinder. Okay, let me scroll. How do I clear? I repeat the conjecture on this slide. The equality would occur here. It would occur, so hopefully it would occur only in these cases if KNL are actually those round case cylinders falling into some specific, whose measures fall into specific interval of measures. So equivalently, here is a more explicit version of what are those intervals, what are those coefficients. The explicit form is written here. And again, it's with the special functions. I know it's a little bit scary, probably difficult to follow, but I believe that this is the explicit version of the conjecture. Here are some pictures. So again, the explicit version of the conjecture, it's completely clear where it came from, right? Because we needed to prove some inequality of f double prime over f prime, and we needed to estimate it from below, right? So solving some ODE, we just get that this is what would be f double prime over f prime under the second integral. So here are some pictures of the special functions. If we draw S1 and S2, S1 and S2 are functions which stand for surface areas of K round cylinders. You see that most of the time in dimension 2, at least, the ball wins. Here S2 stands for just the Gaussian surface area of the ball. S1 is the surface area of the strip. So the ball has smaller surface area in dimension 2 at least than the strip most of the time, but then at some point they switch. Similarly here, I draw these functions phi1 and phi2. At some point they intersect, and at some point phi1 becomes smaller than phi2, even though it doesn't seem like that from this picture. So here is one progress that's known towards this symmetric isoperimetric problem of Morgan, Haleman, Bart, and O'Donnell. It was done by Barchesi and Julien in 2018, and they showed that indeed the isoperimetric inequality in the case of convex sets, and I'm really studying this question for convex sets only. They prove something more, of course. But the isoperimetric inequality for convex sets of sufficiently large Gaussian measure is attained by strips. If the measure is very close to 1, strips will be the minimizers. So this is, of course, yeah, really remarkable result. I'd like to mention that this symmetric Ehrhard conjecture would actually imply that result. So it would, if that inequalities that I said would be true, then we would be able to conclude that indeed strips are minimizes for sufficiently large measure. This, of course, is not so exciting because we know that it's true anyway, but still it's good to know that this conjecture is, it implies something that's true. As a sketch of the proof, I'm not going to go through it, but roughly it's kind of similar, very similar as Ehrhard implies isoperimetric. So again, we can show that for sufficiently large for sufficiently large measure, our function becomes just phi inverse, where phi is the symmetric version of the CDF, symmetric CDF. And again, using concentration, we can show that we can compute the limit explicitly and take derivative, and yeah, it happens to be the surface area of the strip. Question is whether this inequality, the symmetric Ehrhard conjecture, implies isoperimetry always. It's kind of worrisome. I don't know how to prove it. It's clear that this global version, this argument, as I said, the one that helps to show that Ehrhard implies isoperimetric inequality, or what I just said just now, it doesn't work in general, and for a very good reason. You cannot just take the radius of your ball and blow it up and send it to infinity and hope that you get something sharp when you're studying sets of fixed small measure, because equality is not attained for round cylinders which live in different intervals somehow. It's yeah, it doesn't quite work. At least, yeah, I wasn't able to make it work. But somehow I'm hoping that still there is some local argument. There is a way to look at the local form of both conjectures and conclude it. And yeah, I wasn't able to. So I haven't thought that much about this Gaussian isoperimetric inequality. Maybe some people who did would see it much faster. But yeah. Another thing, let me remind you, another very nice thing that we know for symmetric sets in the Gaussian measure is the S inequality of Dirichlet, who showed that whenever we have a symmetric convex set of measure A, then for any dilation, for any t bigger than 1, the measure of the set grows faster when we dilate it than if the set was a strip. So gamma of tk is bigger than gamma of t times the c1. I'm trying to be consistent with my notation. It's just a notation for the symmetric strip of Gaussian measure A. And the symmetric Ehrhard, again, if we were to assume that it holds, then it would imply this S inequality of Dirichlet on a very large, on a very small interval near 1. So whenever the measure is very large, whenever we're talking about strips, it would be true. So again, it implies two statements that we know are true. Maybe it's a good indication that it is indeed true, at least on that interval, kind of very far away. Another thing I've been, I just wanted to point out, because our conjecture, it's not just about strips, right? It's also about the cylinders and balls. So here's one thing about balls. Balls I will denote, balls of Gaussian measure A, I denote using all this notation Cn of A. So if symmetric Ehrhard conjecture holds on the plane, and if we additionally assume that the symmetric isoperimetric conjecture holds, which I cannot improve that one applies the other, right? Then for there is some interval, at least on the plane, in R2, there is some interval of measures, so that for all symmetric convex sets of those measures, the average mean curvature with respect to the Gaussian surface measure is maximized on a ball. And what I wanted to ask, I think it's a curious, legit question. Maybe this is just always true, and maybe it's even easy. I don't know. Is it true that the average mean curvature for any convex set with respect to the Gaussian measure maximized on a ball? Or maybe it's not true. Who knows? Okay. Let me slightly switch gears. Any questions so far? Everyone is very quiet. Am I being too fast? Maybe I'm being too slow. Okay, so let me recall, and of course I will go back to the questions that I'm talking about in just 1 minute. Let me very briefly make an interlude and recall the dimensional Minkowski conjecture. So in 2007, Galyna Livshyts conjectured for even, actually they conjectured for Gaussian, we conjectured it for even together with cosine imbecility. for even log concave measures and symmetric convex sets K and L, the measure to the power n is 1 over n is concave. So the function for which this concavity property holds for any even log concave measure is t to the power 1 over n. That function always works. So Cauchy-Nayyar showed that the symmetry assumption here for symmetric convex sets are important if you simply assume that the sets are convex, but and assume that you have origin in the interior. It's not enough, even in the Gaussian case on the plane. We studied this question with Crescenti Marsigletti, showed that the true near ball for rotation variant measures using this local approach. Like I said, this is where we kind of started it. Together with Marsigletti and Zwabic, we showed that this conjecture actually, as weird as it looks, follows from this celebrated Minkowski conjecture, which I have no time to talk about at all. But that one really does not look weird and looks natural. So that's a strong indication that maybe it's true. People somehow really do believe it's true. In the paper with Kossel and Kolesnikov, in particular, among other things, we also kind of strengthened that implication and showed a bunch of things, but we showed that this implication works from LP Minkowski inequality to the Minkowski inequality in the additive form. So it's very important to understand that it's in the additive form. And in other words, knowing for Lebesgue measures that some LP Minkowski inequality holds does not imply this conjecture ever. Because don't want to say too many things. If somebody wants to ask, I can explain. Okay, anyway, together with Sasha Kolesnikov in 2019, we showed that if the measure is Gaussian, that and K and L are convex sets containing the origin only, then instead of 1 over n, you can take 1 over 2n. It's worse. 1 over n is the bigger the power, the better, because it's kind of more concave. But it holds for all sets containing the origin. Last year, Kenazis and Mashkidis showed the remarkable result that this conjecture holds for the Gaussian measure with the optimal power 1 over n. So that's what's known. Let me, before I get back to the Gaussian measure, which is a primary subject for sure of the talk, let me just mention a few results that in the paper I got about general log concave measures. So one thing is I proved that for any log concave even measure and for any pair of convex symmetric sets, for some powers that's maybe very small, we have this dimensional inequality. Indeed, we can raise it to some power, and the power that one can take is n to the power minus 4 minus or small of 1, which is or small of 1, of course, is very obvious to everyone. I hope where it comes from. Current bound for careless conjecture. If it wasn't for Yuan Zichen's recent result, I would have had n minus 5 here. Yeah. So yeah, like I said, previously there was no bound at all known in general for all log concave measures. I forgot maybe to say for unconditional. Sorry, for unconditional it was known with 1 over n a long time ago, thanks to work of Christos Argo. But yeah, for general log concave measures it was not known. Then in some cases this result improves. So if we consider measures with potential P norm raised to the power p for p between 1 and 2, we have something that's close to 1 over n. It's constant over n times some logarithmic term. In the case of rotation invariant log concave measures with exponential densities, as written in theorem 2 here, we have something with 1 over n squared instead of 1 over n. But actually, this 1 over n squared improves to 1 over n plus or small of 1 in the case when p is between 1 and 2. So this is the case because there is this very beautiful correlation inequality that holds both for rotation variant measures of this form when p is between 1 and 2, and for product measures as considered in theorem 1, but p is between 1 and 2, as was proved by Ignatius, Cauchy-Nayyar. And Alexander pointed it out to me that actually they don't only know that property for this product measures, but they also know the property of rotation-oriented measures. So, there is a paper of Bart and Clardag where they, using that correlation inequalities, they deduce that they deduce something about Poincare constants of restrictions, and they also have a simple argument that reduces the Dirichlet to Galyna question. Okay, so any questions so far? Let me mention now a tighter question. So the dimensional Minkowski conjecture was about putting some fixed power and the studying inequalities of that type. Now, what if we allow the power depend on the measure of sets K and L? So what if we want to show instead that for all sets K and L are convex symmetric of measure at least A? We have this inequality with some power that depends on A. Then what is the tight bound on this power when A goes between 0 and 1? Equivalently, well, not equivalently, we can also consider this thing locally associated with one convex body. So we fix a convex body and we look at all the local perturbations of this specific body with various sets and raise it to very specific powers. And we want to take maximal powers and works with this specific body. Because of law concavity, one can actually show that this symmetric powers for measure A is infimoral powers for sets K. So the point is that, of course, it's exactly the same thing as asking what is the optimal function that gives us inequalities. There is direct connection. I don't want to get too much into the details of this, but there is a direct, of course, connection. And because of Ehrhard's inequality, even without symmetry assumptions, we can say that this power is bounded always by something for any fixed A. But of course, not for A equal to 0, but for any fixed A. And it tends to infinity when A tends to 1. So that's a very strong sense that the Ehrhard's inequality yields. It's interesting that if you analyze the results of Sasha and I, or Ashkenazis and Moschidis in both cases, so what Sasha and I did implies that the power tends to 1 over 2n when A tends to 1, and the Ashkenazis Moschidis power tends to 2 over n. So here is another result. One can prove some bound in the case of the Gaussian measure, and show that basically the concavity power corresponding to this bound, again, it's difficult, of course, to say everything. Hi, Dima. It tends to infinity. And as a consequence, actually, of this result, which we would not be able to get the consequence without somehow part of this estimate being strong enough, we get the version of Minkowski first inequality for the Gaussian measure stated here. So people who do Minkowski theory might find just this little thing curious. And I don't know, maybe it could be useful sometime. I don't really know. I wanted to mention also that in the non-Gaussian case, if we assume that the measure is strictly law concave, meaning that the Hessian of the potential is bounded from below everywhere by some multiple of the identity. For measures like that, also we have the properties that the power tends to infinity. And okay, that was about a bunch of stuff. Let me finally, I've already been talking for half an hour. I finally got to the main result of the talk. So let me now talk about this. Any questions so far? Maybe I'm trying to do too many things at once, I don't know. Okay, so the main thing, at least what I consider the main thing, apparently not everyone, but what I think is important is that I can estimate this power, symmetric concavity powers, that, like I said, if it's estimated optimally for every set K, we have immediately the symmetric Ehrhard inequality. So we would like to estimate it optimally depending on the measure of K only. So I was not able to do that. I wasn't able to estimate it depending on the measure of K only, but I was able to get an estimate for that quantity in terms of a second moment on K, first moment of the norm of K, second moment of the norm of k, and the in radius of k, where q here is some rational function of power 2. In other words, it's a ratio of some polynomials of power 2. And what's important about this is that the equality holds if k is a round cylinder. If k is that thing that's a product of a ball and a space. So this is somehow the key feature of that result. You know, particularly it might be strange that there would be equality attained when we have the in radius here. You know, whenever we have in radius, how can there be equality attained? But no, in this case it is attained. If you want the specifics here, the specifics is not very nice. Let me go through it quickly. Let me mention that because of that, we know exact value of this concavity power for symmetric concavity power for cylinders. Again, we can write it explicitly in terms of these functions. I know it probably looks a little bit horrible, but if you're used to it, it's not so bad. The idea of the proof here is that on one hand, because of the theorem, one can, well, roughly speaking, one can show the lower bound for the symmetric power of cylinders from below. And on the other hand, one can prove a matching upper bound for the concavity power by just taking a very specific flow, by taking very specific pairing body, which is also a cylinder, roughly speaking. So if by just considering dilates, we've estimated power from above and it matches, it's the same thing. So roughly speaking, because of that, we conclude that the conjecture is kind of optimal in a sense. It can be, one cannot hope that something better holds. One cannot hope at least that that lower estimate we want to get would be better than that, because definitely for every a minimum of these guys will be one of the results for that thing. You cannot hope for anything better. So naturally one might ask if it's possible to minimize this horrible expression of one-goal convex sets and show that it's minimized by what we hope it is, which would give the result for symmetric Ehrhard conjecture. I don't think it's so bad, you know, technically, I think at least on the plane, you know, it could be not so bad. Maybe scroll back one step, but outside of that, it's actually not terrible. But in principle, I'm actually just wanted to outline an even simpler question, how to bound moments of the norm of k raised to the power p. Even that I don't really know. Okay. So let me now talk about the briefly, basically. So this is the main result. Here it is. I'm going to talk about a couple of ingredients of the proof in a very, very vague terms. Stop scrolling. Okay, here. Any questions so far?
Can you go back a slide, Galyna?
Yes, Hiron, what would you like me to do?
Go back one slide.
Yes.
So you want to show, so you think maybe the inequality written above might be true?
Yes, I hope so. I think it might be true. Yes.
I guess there has to be.
It doesn't have to be, but so
no, for cylinders there has to be an equality just because you say this would imply the symmetric Ehrhard.
Yeah, so for cylinders,
but somehow isn't it true that if you get a cylinder and I don't know, like chop it with a slab or something, I guess you can make the inner radius decrease by a lot without affecting too much the other quantities.
You think?
No, I'm just, okay, I don't know, but like the inner radius looks like a pretty sensitive quantity to me.
Yes, I agree with you. So, okay, that's what I said. So, okay, so it's easier to state. Like I said, if I psych myself up to try and prove something like this, I will not use inner radius. I will go one step back. And one step back, instead of the inner radius, it's just expected value of the gradient of the norm squared. Which, so if you take k norm and you take the gradient, you know that it's bounded by the in radius, right? Because it's on the polar.
Yeah, okay. And like what's the role of symmetry here? I'm not sure I completely followed. So none of this is true if can you generalize this if the body is not symmetric, some other quantity?
Well, yes, Ehrhard did it in 19 something. So Ehrhard's the best in the non-symmetric case, I believe, at least in general. None of this is true without symmetry.
Sure. But for what you, okay, never mind. I think I'm not completely following. So continue, and maybe I'll ask in the end.
Sure. So for everything I say, symmetry is important. Maybe not every single statement, but it's most of the time it's assumed and it's important. Yes. But thanks for asking. Let me say a couple of words about this nice guy called torsional rigidity that's been known for a couple of 100 years, and people have studied it in great detail, particularly for the back measured for Laplace operator and for P Laplace operator, fractional Laplace operator, for all kinds of stuff, but not so much, well, much less for in the Gaussian case. So torsional rigidity is defined as the supremum over all, let's say, all functions which vanish on the boundary of this ratio that's written here. We fix a function f on k, we integrate v against this function f, divide by the integral of the gradient squared, assume that v vanishes on the boundary. This is what's called torsional rigidity. Very easy, very cool thing that one can prove is that this supremum actually equals to the infimum of the integral of the gradient when of such functions such that Lu equals to f. So it's the energy of this equation Lu equal to f, where f, yeah, like I said, that function that we fixed. Rephrasing it, we can say that the average energy, so the integral of gradient function is always bigger than the torsional rigidity if Lu assumed to be equal to f, and the quality is attained if and only if U is zero on the boundary, which exists and is unique in the cases that we consider. One of the ingredients of the proof that I wanted to kind of mention, because I think it's cool, or I don't know, just wanted to mention, there is some stability estimate also in this result. If we assume that the integral gradient of the function is very close to the torsional rigidity, then indeed maybe it's not constant on the boundary, but its variance on the boundary, restricted on the boundary, is pretty close to zero. Does not depend on the size of the set also. So now with this torsional rigidity, actually there's another result, and this is kind of what implies, of course, the previous result is that this concavity power estimate works with double torsional rigidity of any function f with integral 1 minus the variance of f plus this additional thing that depends on the second moment. And the equality in this guy also holds if and only if k is a round cylinder. And this result implies the previous result in view of this lemma that helps us estimate torsional rigidity. And the idea here is that, remember, torsional rigidity, it's something that takes, it's a supremum of things where function takes value 0 on the boundary. So if we take supremum, we can estimate it from below by taking one specific function that takes value 0 on the boundary. Specific functions that we take is 1 minus norm k squared. Miraculously, it happens to be sharp for cylinders. One can estimate it in some reasonable way for cylinders. Also, taking f1, one can get the other bound that I mentioned. I'm almost out of time. Another ingredient of the proof, it's not quite, I just wanted to mention that one can also show, one can characterize the equality cases for the Brascamp-Lieb inequality. So here is Brascamp-Lieb inequality in specific convex set version written out here. So one can prove that the equality here holds if and only if k is sort of cylindric and f is of the forms that's written here in certain specific direction. In the Gaussian case, it was known before, and Caffarelli's theorem, so Chafai and the Heck showed it from Caffarelli's theorem. It also says that people showed some things for this as well. And the nice advantage about working with Caffarelli's theorem is that you don't need to assume smoothness. For what I did, you need to assume smoothness, and so I had to do the stability version and the approximation argument. I also wanted to highlight the stability version of it in the Gaussian case. Here it's highlighted. I have no time to talk about it, but somebody wants to read the slides, I can read the slides. And just the summary is that I wanted to say that where do round cylinders come up? They don't come up because we want them to come up because they already come up in the other conjecture. They come up because of the proof of this theorem. And cylindriness comes from the equality case characterization of Brascamp-Lieb. And roundness comes from the fact that we have to deal with some quadratic functions which are constant on the boundary of the set, and the quadratic function is constant on the boundary of the set if it's a round cylinder. So that's sort of the summary. I'm not going to talk. I talked about the proof of you last week, so I prove in the smooth case only. Thanks for your attention.